First remind what we did 2 days ago. This was to talk about Markov chains and PCTL star model checking. And this picture is just to remind what is a Markov chain. So I think the simplest way to think of a Markov chain is take a directed graph and attach probabilistic distributions for each state for the successor states. So instead of having a non-deterministic choice, we have probabilistic branching. This is to remind the syntax of PCTL star. So on the state formula level, we have propositional logic. And here on the additional ingredient is a probability operator that takes 2 arguments, a path formula, stating a property that a path might fulfill or not, plus a probability interval I, with not stated here, with rational bounds, lower and upper bounds. And from the path formula level, we have propositional logic, and the atoms here are state formulas, and the 2 basic modalities are next and until, so we take it from standard LTL. So you can think of the syntax of path formulas to be as LTL. The only special thing is that for the atoms, we use state formulas. And for the PCTL star model checking procedure, so what I sketched was a procedure which is very similar to the one that is known for CTL star or CTL or other branching time logics. So you simply follow the inductive definition of the satisfaction relation to evaluate inner formulas first and to compute their satisfaction sets, the set of all states satisfying this particular subformula. And for the treatment here, or for the propositional logic fragment, that's the trivial thing. So conjunction corresponds to intersection, negation means taking the complement. And for the probability operator, we do the natural thing. We compute the probabilities of given a state, we compute the probability satisfying this particular path formula. And then we simply compare this value with the probability interval I. And in case that phi is indeed some complex formula which uses a combination of next and until, then we had this big picture, which is shown here. So we first, by simply replacing the inner subformulas with fresh atomic propositions, we obtain an LTL formula. Then we can rely on standard techniques that you heard about this in Javier's talk and will hear more about this, to generate a deterministic automaton. Here I used the Rabin condition, but you can also deal with some other kind of acceptance condition. And then the remaining step is to combine the Markov chain plus the automaton and reduce this verification problem to a probabilistic reachability problem. And the latter thing can be computed using a linear equation system in the product. From a complexity theoretic point of view, the expensive step is sitting here, going from LTL to a deterministic automaton. This in general can cause a double exponential blow up, and what I mentioned in the panel is that this is not optimal. There are better algorithms which do not use deterministic automaton, either some other kind of automaton or this automata-less approach by Kokobetis Yannakakis. Well, what we do today is to talk about Markov chains with rewards. So we are going to attach values to the states and want to reason about weight-bounded or reward-bounded properties and long-run averages. So we'll start with reward functions that assign to each state a natural number, and this is not consistent in the literature. I'm going to use the word reward function for a function that assigns non-negative rewards values to the states, and the notion weight in case then we deal with integer weights, which can also be negative. Well, what we do is to talk about the accumulated rewards. So if you have a finite path, S0, S1 to Sn, then we simply collect all the values of the rewards that we have seen on all the states. While this excludes the last state, so the idea is you earn a reward when leaving the state. So you have seen this simple example of a Markov chain with 4 states 2 days ago. So for instance, if you take this path, start, try, lost, try, delivered, then and with this annotation of the rewards, where we simply count the number of trials, then you see 2 times the state try, which means the accumulated reward is 2. Now, typical measures of interest using such Markov reward models are reward bounded until or eventually properties. So for instance, you might ask, what is the probability to deliver a message within at most 3 trials, which means you can attach a reward bound less or equal 3 to the eventually or to the until operator. And another thing is to talk about expectations. So I use this diamond plus symbol to indicate the random variable that assigns to each pass the accumulated reward that you earn until reaching this delivered state. And then with this E, I mean the expected number, in this case, of trials until delivering the message. Now, in PCTL, you can extend the syntax. So far, we just have the pure until operator on the pass formula level. So you can add until with reward bounds, for instance, in this form. And you can also add an expectation operator on the level of the state formulas. And here, as we did in the probability case, so we attached here an interval. You can attach here an interval as well. I just used here less or equal r, with r being some rational number. And here this plus operator, with the meaning that a state S satisfies this formula if and only if the expected accumulated reward until reaching a phi state is bounded by r. Now, going back to this example you have seen before, for instance, you might deal with a specification that requires that the probability to deliver the message within 3 steps with probability at least 0.9, or the expectation until delivering the message should be bounded by 5. So let's talk now about how to compute or how to evaluate such formulas. And again, as in the standard PCTL model checking procedure, we evaluate the inner formulas first, which means you can assume that you know the satisfaction sets for phi 1 and phi 2, so you can treat them as atomic propositions. And the procedure does a very naive thing. So if the reward bound is r, some natural number, then we simply compute. Yeah. With the reward bound, well, it is you take all the infinite passes that satisfy phi 1 until phi 2, and where the accumulated reward until, for the shortest prefix satisfying phi 1 or yielding a witness for phi 1 until phi 2, you require that the accumulated reward is bounded by r. Well, in this context, I describe how to compute this, assuming that you know the satisfaction sets for phi 1 and phi 2.
Because somehow I missed why you need the automaton. Usually you need it for the...
Let's say, in this context, I don't need the automaton at all. This was just to recall what I did 2 days ago. But in this context, when dealing with these 2 operators, I assume that the satisfaction sets for phi 1, phi 2, and phi are known, in which case it doesn't matter whether it's a PCTL star formula with or without rewards. But I'm not using automata to evaluate these formulas. Yeah, going back. So what we do is we successively consider the reward bounds I equals 0, 1, 2, and so on until r, and compute the probabilities for satisfying phi 1 until phi 2 with reward bound I. And here we heavily rely on the fact that, or on the assumption that the rewards are non-negative, which means if you consider an infinite path and the set of finite prefixes of an infinite path, then the accumulated weight will increase. It will never go down. It will not oscillate. So that's what we use by this naive computation, by just considering increasing reward bounds.
I don't understand why you are not using automata here, because it's very easy to build, because there are no negative, it's very easy to build an automaton that just simply counts what's the accumulated weight, and use the previous algorithm to do it.
this is what I'm going to present here is the same. I didn't formulate it with automata, but the effect would be the same. Indeed, what we do is let's call this value, this probability x as I, and what Moshe was saying, and this is completely right, you could also think of this Si to be a state of an automaton that attaches to each state the reward that has been accumulated so far. And then you can just look for the reaching a phi state where the reward bound, you just can let's say these states where you go beyond this reward bound could be declared to be terminal states, bad states. And then we get an equation system, a linear equation system. So for the states that have at least one path satisfying phi 1 until phi 2 without being a phi 2 state, and we suppose that I is greater or equal than the reward of S, then we say XSI, this probability, is this weighted sum, and here for the weights we take the probabilities to move from S to S prime within one step. And then from state S prime we look for the probability to satisfy phi 1 until phi 2, and with a modified reward bound, namely I minus the reward for state S. And for the phi 2 states, then we simply say this probability is 1. We always satisfy this formula because we are already in phi 2 and we do not need any, or let's say the accumulated reward is simply 0. And in all other cases, so for the passes, for the states that do not have a path satisfying phi 1 until phi 2, and not satisfying, this is the remaining case, then we simply say that the reward, this value here is 0. Well, and then this is again a linear equation system, and it has a unique solution. And well, in this case here, if the reward of state S is 0, then this means we stay on the same level. Then you also have here value I, which means that you also have a linear equation system, as you have seen for the case of eventually properties, but with this assumption that S has a path satisfying phi 1 until phi 2, we again obtain again that this linear equation system has a unique solution.
The advantage of also using automata here, because then you'll equally be able to do it for PCTL star with rewards. Because you can have nested formula with rewards.
But it doesn't matter. Let's say I wrote here PCTL, but this could also PCTL star. As soon as you treat them as atomic propositions, the phi 1, phi 2, it doesn't matter whether these are PCTL star or
not if you allow nesting, not if the feature in itself have formula with rewards.
This doesn't play any role because we evaluate these formulas first. When we treat this formula here, then we suppose that the satisfaction sets for phi 1 and phi 2 have been computed before.
But imagine there are no rewards. There's no easy way to reduce evaluation for PCTL star to just PCTL evaluation.
No, that's right.
And so there's no easy way to do this. So there's going to be no easy way to do it once you add rewards as well. And I'm saying if you think in terms of automata, then you could just add rewards to every until.
And I'm saying this makes no difference. Well, you can, whether you consider this as an equation system that you obtain by constructing first an automaton or not, you will get the same. Let's say it would be a different way to write it down, but it will be fairly the same equation system. I have nothing against using automaton here. I'm just saying.
I don't know any other way to build the equation system other than using automata.
Well, this is an explicit way I wrote it.
Can you do the same thing? Forget about rewards. Can you construct equation systems?
Well, there is one at one
without automata.
Sorry?
Do you have a way of creating an equation system for PCTL star without using automata?
Let's say, when I consider this formula, then there is no
PCTL star. This is PCTL.
But I and let's say what I was presenting here, we never construct a full automaton for a PCTL star formula with nested probability operators. We treat inner probability operators first. So there is no big, at least not in the approach I have presented, there is no big automaton for the full formula.
Also, but also for CTL star, what is done is to partition the formula into subformulas.
But how do you deal with this? How do you deal with the LTL formulas?
You partition it to subformulas which are CTL, and then you can use CTL.
I don't know.
And then you get
If you have a way to reduce CTL star to CTL without automata, I'd like to know.
And then you have a subformula. Once you treat the...
Oh no, it doesn't work.
I
We
did
don't
say
know.
there is no automaton, but it's for subformulas which are referring to a
Yeah.
subformula and LTL subformula, where you already treated the sub formulas which are CTL beforehand. So what Christel is doing here is to say we treated the sub formula beforehand, and here
Yeah.
I replaced the automata part with equations.
Yeah.
So
Let's take
this
it
is what
offline.
is here. and
Yeah, okay.
it's done for general CTL stuff.
Thank you. Well, but one argument, well, I like automata as well, but there is one argument against using automaton. If this reward bound is very large compared to these reward values, let's suppose they are just 0 and 1, maybe 2, and this is a huge number, then to evaluate this, you can deal with some certain reward windows. Do you know what I mean? I mean just the maximal window size is the maximal reward value. So if the rewards are just 0, 1, then you just need to remember the values for the last 2 levels. So then it would be more memory efficient to evaluate this rather than building the full automaton. But I have nothing against automata. I like them as well.
You can do just LTL probabilistic model checking without automata, other than Kubernetes and Akakis.
Yeah.
I'd love to know.
Okay. Well, I don't know. Okay, and for the treatment, this was the treatment of the probability operator with reward bounds for the until or eventually operator. And for expectations, the world is even a bit simpler. It is a single linear equation system with one variable per state. And this is a very natural thing what we do. So suppose we deal here with this expectation operator until reaching a phi state. Now everything this is a bit unpleasant. There is a side constraint that we need here to make sure that this expectation indeed exists. And the side constraint we make here is that indeed with probability 1 we will reach a phi state. In which case we can have this linear equation system as follows. For the phi states, for all the states satisfying phi, the expectation is simply 0 because we are already there. And for all other states, we take this value here, which means we need to leave state S in either case, and in all these cases we earn the same reward, namely the reward attached to S, plus the weighted sum for all the successors S prime of state S, multiplied with the expectation from state S prime. And again, well, thanks to this assumption here that indeed from each state we will reach a phi state with probability 1, this equation system has again a unique solution, and this one agrees with the expectation. And this approach here with this equation, that in this case we do not need the assumption that the rewards are non-negative integers. This can be arbitrary rational values. Let's go back to the time complexity. So for the expected rewards, this was one linear equation system with one variable per state. So this one is solvable in time or computable in time, polynomial in the size of the Markov chain. For the reward bounds with this naive loop here, we obtain a procedure that is polynomial in this value R plus the size of M. But this value r, if you suppose that it is given in binary, so as a bit string, then this is not a polynomial algorithm, it's a pseudo-polynomial algorithm, or exponential in the logarithmic length of this value r. Now, short comment on this. So this was the general case where we have this pseudo-polynomial algorithm. In the case that we have unit rewards, which means only the reward values 0 or 1, we can do slightly better. There is an approach, well, I know it under this keyword, repeated squaring. So suppose r is 2 to the power of k, then you can split it. You look for the probabilities maybe it's easier for eventually. you look. This is you want to reach the state, phi state within 2 to the power of k steps. Then you split in between after you earned reward 2 to the power of k minus 1 and look for the probabilities being in one of these states, and then you can do this in an iterative way. So this only works correctly because then if you have only reward values 0 or 1, then we know along all the passes satisfying this constraint, there will be a state in between where we have accumulated the reward exactly 2 to the power of k minus 1. And this does not apply in the general case where the rewards can be 3 or 4 or something like that. Well, and indeed, this is not a problem with this, that we have here this exponential or pseudo-polynomial algorithm. And indeed, this problem has shown to be computationally hard. So there was first an NP hardness result by Larusini and Sproston. And later on, there was a better characterization of the complexity by Christian Haase and Stefan Kiefer. So it is somewhere between NP and P space. Yeah. It has been considered, and now you ask what happens here. I'm not sure whether this has been considered, the computational complexity. I have no answer, I'm sorry. Whether discounting, if we do the same thing here, but with discounting rather than just taking the normal sum. And well, you can, let's say the algorithm I presented, this pseudo-polynomial, you can adapt it. That's not the problem, but I don't know about these bounds. I'm not aware that this has been discussed. Yeah. Well, POS stands for positive. I don't know for the letters SLP. Well, the question is you have an arithmetic circuit with gates that stand for addition or multiplication, and the input is some integer value, and the task is to check whether the output can be positive. But does anyone know the meaning of these letters SLP?
Pseudo-linear polynomial.
Okay. So this was the case of non-negative weights, or what I called rewards. And for the expectation, this was different. I mentioned that it also works for weights. But for this naive algorithm to compute probabilities for reward-bounded properties, we heavily relied on the monotonicity. And this breaks if we deal with weight functions in the sense that they assign integer values, possibly negative and positive values to the states. Well, as I just mentioned, we have seen for the expectation operator, there is no difference. It works fine. Now, what is about weight-bounded reachability? Let's first, look for decision problems. So here, let's consider 3 versions. You might declare some states to be gold states or just a single state, and you have some distinguished state S, some reward-bound R, and you might ask whether the probability to reach the goal while the reward, with reward-bound R, whether this probability is positive, whether it equals 1, or whether it's beyond some threshold, let's say 1/2. Well, indeed, all these problems are still decidable, and The first one is a trivial one because this is an ordinary graph problem. You just need to check what is the shortest path going from S to goal. Just run standard graph algorithms, Bellman-Ford or so, to check the existence of such a path from S to goal where the reward is at most R. The almost sure case, well, this is again solvable in polynomial time using shortest path algorithms, but it's a bit more tricky if the goal state is not a trap, by which I mean, so if you can leave the goal state and cycle around and return to the goal state, in which case you might visit it first with some reward where the reward is larger than R, and then you might have the possibility to return. Well, if there's time at the end of my talk, I can come back to this, how to do this. This needs some tricks for this case. Well, even the quantitative case where you have here some rational number or 1/2, it is doable, but it is much harder than in the case of non-negative weights. So I will not present these algorithms here. The idea is to encode this probability using quadratic equations, and then you can rely on the existential theory of the reals to come up with a decision algorithm. So what we do here is to borrow ideas that have been invented for probabilistic push-down automaton or probabilistic one-counter machines. So it's doable, but it's much harder than in the non-negative case. And well, you might ask, so here I mentioned only results for decision problems. Can we compute these values? I cannot give an answer. I'm not aware of an algorithm, but if so, then you should not expect linear equation systems or something like that. The point is that these probabilities can be irrational. And let's look for an example. So here we have 3 states, S, S minus, and S plus. And the meaning of S plus is that we earn reward or weight +1, for S minus, -1, and for state S, 0. And we want to reach the goal states. And these values Q and P, these are simply parameters for some value. So some rational value strictly between 0 and 1, and the sum should be less than 1. Now
What is
look
the semantics of faded fonts?
of
Faded fonts. Does it have some meaning that this is in?
Uh,
This is faded.
oh well, you can read it better.
Okay.
I like it. That's a good reason, or not? Look now for the probability to reach from S the goal state while the accumulated weight is 0. Now, what are the possibilities to do so? You can go directly from S to goal. This is probability 1 minus P minus Q. Or you can take these cycles to the left or to the right, but the number of taking these cycles going to the left or going to the right must be equal. Because here we get -1 whenever we go to the left, we get +1 whenever we go to the right. So altogether, we can enumerate all these possibilities. This n here intuitively stands for this number, how often you take the cycle going to the left and to the right. And so taking these cycles n times, exactly n times, then the probability is p to the power of n multiplied with q to the power of n. And this 2n over n, this is these are the possibilities to interleave these cycles, or the number of possibilities. And in either case, the last transition must be the one from S to goal, which yields this value. Now, okay, we have here some infinite series, and now you can do some clever calculation, or you can ask Wolfram Afra, what is the result? So you get this result, and with this square root, by plugging in appropriate values for P and Q, you obtain an irrational value. Which means, well, there might be some algorithm, let's say if the task is to compute the ith bit of this probability value, there might be some algorithm, I don't know whether there is one, but you should not expect to have an algorithm like as you have seen for the case of non-negative weights.
You should be able, just by iterating the quantitative decision problem, to be able to do kind of binary search and get the height bit, right?
Yeah, you're right.
Yeah.
You're right. You're right. Yeah. Yeah. Does this? Well, you can certainly approximate, but.
Well, by just sharpening enough an interval above it, you should be able to, I think, narrow down the height bit just by sharpening the same idea that you had before. By just sharpening it, you should be able to get any bit, but
yeah. Okay, well, and now you might ask whether this is some special thing, because I wrote here equals 0, but you have the same phenomenon if you deal with reward bounds less or equals something, simply because you can, this value here is the difference between the values, the corresponding values, where we have the upper reward bounds 0 and -1. And then, which means that at least one of these values must be irrational. And I guess you can come up with an analogous formula as you have seen before. So let's talk now about mean payoff or long-run averages. So first, what is the mean payoff? So you can take an arbitrary graph with weights for the states and consider infinite passes. Then you can define the mean payoff either as the largest or the smallest cluster points, or the lim sub or lim inf, when you sum up the weights for all the finite prefixes. Well, the first observation is if you start with an arbitrary weighted graph, finite, then this lim sub and this lim inf need not to be the same, which means that even that the limit need not to exist. And here's a simple example. Well, I didn't depict the graph, but suppose you can switch between two states, S and T. State S, there we get the weight +1, and for T we get -1. Now, to generate such an infinite path where the lim inf is strictly smaller than the lim sub, so follow the following strategy. So first we stay, let's say, 1 time in state S, and then 2 times in state T. Then we jump from value 1 to value -1. Then stay in state S, stay there as long, and make sure that the value gets positive. And then as soon as the value is positive, so let's say this was n2 times, then you take k2 times, you stay in state T to make sure that the value drops below 0 again. And so you can make sure that these values indeed oscillate, which means that the lim sub would be strictly larger than the lim inf. However, in finite Markov chains, if you look for the expectation, then it makes no difference whether you deal with the lim sub or the lim inf. And we will see, we will see this in more detail. I mentioned this 2 days ago. In a finite Markov chain, almost surely we will reach a bottom strongly connected component and visit all its states infinitely often. And even stronger, with the same long-run frequency. Almost all paths enjoy this property. They agree on this long-run frequency, which in the end will give us that these values agree, and that's a proper limit. So let's have a closer look at that. Let's first introduce this notion of steady state probabilities. So we take the long-run average of the probabilities for being in state S after n steps. So this next I, so you look for what happens where you are after I steps, and we sum from some state T, and then we sum up all these probabilities and we take the average, and then the limit tends to infinity.
Where does T appears on the, what is T? What does it mean for each T?
It does not depend on T. This limit is the same whatever state T you pick, provided that you talk about a strongly connected component, a bottom strongly connected component, or a strongly connected Markov chain. This is the meaning of the T. So you can say some T but then the same value, you will get the same value for each t. Well, and these values are inside some bottom strongly connected components. These values are computable, again using a linear equation system, and these are the so-called balance equations, stating roughly what flows in, flows out. So what flows out is this steady state probability, so the probability mass on the long run flows out of state S, and what flows in, well, take all the predecessors of state S, this time we go backwards, and take their steady state probabilities and then the weighted sum. Well, if you take this alone, then this equation system would have many solutions, but with the side constraint that these steady state probabilities indeed constitute a probabilistic distribution, which means their values sum up to 1, then this one here yields a linear equation system which is known to be non-singular, so it has a unique solution, and these are the steady state probabilities. Now, one step further, and what also has been shown, whenever, or for almost all passes that eventually hit this chosen BSCC B, then we know that the long run frequency of state S, by which I mean that you take the number of occurrences of S in a prefix and again the long run average thereof, then this value is nothing else than the steady state probabilities. And this holds for almost all passes, which means with probability 1, almost surely all the infinite passes, they have the same mean payoff, which then gives you that this lim inf and lim sub are the same. It's simply the limit. Well, and this means now that if pi is an infinite pass that eventually hits B, then almost surely we can say that the mean payoff, now I can drop this lim inf or lim sub, it's a proper limit, it agrees with this value that you obtain by taking the weighted sum of the state probabilities of the states in this chosen BSCC B times the weight of state S. Well, and this value here does not depend on state S, it only depends on this chosen BSCC B, so let's call this is the mean payoff of B. And now the expected mean payoff, if you have some state S0 in your Markov chain, you might have several bottom strongly connected components, then you can simply compute the probabilities to reach each of the BSCCs B and multiply this with the mean payoff of this BSCC and take the sum thereof. And then this is the expected mean payoff from state S0. Okay, let's look now for long run ratios. So suppose we are given a Markov chain with two reward functions, what I called here cost and util for utility. So let's first long run. So given an infinite path, then let's consider the limit if n tends to infinity, and here we take the quotient of the cost and utility value for the prefix up to length n. Does this limit exist? Well, yes, it does, but it's, let's say, maybe needs some calculation. Well, you can simply just take the same thing here, but multiply the numerator and the denominator with 1 over n plus 1. But then what we have, well, this limit of a quotient, you can write it as the quotient of limits provided that both exists, and this is the case here. If I plug in the limit here for the numerator and denominator, then I simply get the mean payoff for the weight function called cost or for the weight function called util. Well, and assuming this is non-zero, of course. Well, in particular, this limit exists. And now the long run ratio, you can do this very similar thing as you have seen for the mean payoff. So given a path pi that eventually visits some BSCC called B, then almost surely its long run ratio is simply the quotient of these mean payoff values for the cost reward weight function and the utility weight function inside B. And again, this value only depends on B, but not on the particular path pi. And then the expected long-run ratio is simply obtained with the same trick as you have seen before. Just calculate the probabilities to reach each of the B SECs, multiply them with this value here, the long-run ratio of this B SEC, and take the sum. Yeah.
If we define a new function, the ratio between the cost and the utility for every state, and calculate the mean payoff for it, will you get the same thing?
I don't think so. No, I don't. But let's say this would be simply a new weight function. You could simply deal with the mean payoff for this new weight function.
Right. So is there an example for a connected component in which you get something different?
Well, I claim, but I cannot do it immediately, but I think this should be possible, yeah. Let's say I will fail now, but I think so. Maybe I'm wrong, but...
No, I think, there's no reason we should do it. It's the geometric average is not just the
Yeah.
and the mean.
Yeah,
Now,
I think it should be possible to come up with an example. I agree, yeah. Can we do this in the break? Okay, so this... Sorry? Okay, so let's say this was simple, long run. Let's look now for ratios along finite paths. So let's consider just a function, take a finite path, and take the quotient of the accumulated weights for the cost and the utility function, and to make sure that we do not divide by zero, let's suppose that the utility function only has positive values. Now you might look for a thing like this, the probability for the invariance stating that this ratio is always greater than R. And suppose for paths of length 0, so we are just in a single state, define it somehow to make, let's say, choose any value that is larger than R plus 1. Okay, so let's say this is a measurable thing, so that's a well-defined value. Can we compute it? Maybe, I don't know. But well, as you have seen for this example with a weight-bounded reachability, you can come up with analogous examples showing that these values can be irrational. So there might be algorithms to compute the bits of these values, but you should not expect linear equation systems in this very simple form. Well, what is about threshold problems? So if we ask here whether such a value is greater than some rational number q, maybe, I don't know. And I'm not aware that this has been investigated, this problem. An answer I can give in the qualitative case, I mean here if q is 0 or if q is 1, well then of course it's equality here rather than greater 1, then these problems are solvable, decidable, even in polynomial time, and one can even go a step further and compute the maximal or the supremum of all rational numbers R, where this probability is positive or equals 1. And indeed, well, here the supremum, we take here a supremum over rational numbers. It could be irrational, but in this case, in the end, it is not the case. This is a rational number. And let's have a closer look at that. Well, this is the most difficult case. For this case, equals 1. If there's time, I will say a few words more on it. Okay, so let's first look for the inner thing. So let's suppose you have some fixed value R, some fixed rational value R, and how to check whether this value is positive. Well, this inner constraint, the ratio is strictly larger than R. If the ratio is simply cost divided by utility, you can simply do some standard calculation and come up with the constraint cost minus R times utility is positive. Well, and now the good thing is this thing you can define it as a fresh weight function. So if R is fixed, then this is simply, again, a weight function that assigns an integer value to each of the states. Integer, well, if R is a rational, then it might be necessary that you multiply with some integer value. Yeah?
I'm a bit confused. What is the semantics of the probability that always the ratio is greater than R? In my mind, it sounds like something that should be either true or false. Always. The ratio is greater.
You take an infinite path. Well, I defined these values for finite this ratio function over finite passes. And with this always operator, you take an infinite path. And then with the always operator, you range over all the finite prefixes, and then you require this. And for the very first one, where you accumulated 0 reward, you would divide here by 0, just deal with some standard value. And suppose here it would be larger than R plus 1. Or rule it out, this very first value. Yeah?
Could you please go to the next slide? Ratio is cost divided by util, right?
Yeah.
And so these two things have different definition domain. So they cannot be, ratio is not defined from util 0. And
Yeah, as I said, wait 1 second. I ruled out this case. Let's suppose that utility is always positive. That's what I assumed here, to make sure that we never divide by 0. Well, and this constraint here, you can consider it for a single state, or you can consider it for finite passes. And in either case, if you consider this as a fresh weight function, then this still holds for the weight function. Yeah. Which means and then then we are in the case of weight functions, and well, that's what I mentioned before. I wrote it for the eventually. This is doable in polynomial time. I mentioned this before on one slide where I had the decision problems. This can be done using shortest path algorithms. Now, the next observation is that this quantile, this supremum, if you pick some epsilon, then you can come up with an approximation in up to epsilon using a binary search. And the point is, well, you can check this inner condition here. That's what we just have seen. And there are trivial bounds for this binary search. Well, if you suppose that cost and util are both non-negative and the util even strictly positive, then 0 is a safe lower bound, and a safe upper bound is take the maximal cost value divided by the minimal utility value. That's a safe upper bound. So then you have some interval, some finite interval, and you can do a binary search to get an epsilon approximation for this supremum. And we can state the following. The quantile is one of the following 3 values. One of these 3 possibilities is the expected long-run ratio of a bottom strongly connected component. You just have seen how to compute this expected long-run ratio. So just take the mean, the quotient of the mean payoffs of the cost and utility function. Or it can be the ratio of some simple path starting in this chosen state S. And by saying simple, I mean that it does not visit some state twice or more often. Or a simple cycle that is reachable from state S. So it is one of these values. That's, let's say, the set of all these finite passes, all the simple passes. That's exponential, but we are talking now about a finite set of passes. Well, and if it is one of these values, each of these values is a rational number, which gives us that this supremum cannot be irrational. It is always a rational number. And we can now compute it even in polynomial time using the continued fraction method. And let's sketch me how this works. So we have seen that this value is rational, which means we can write it in the form c divided by d with natural numbers c and d, and the denominator is positive. And we can provide a bound, an upper bound for the denominator, which is the max of the maximal denominators of these long-run ratios for the bottom strongly connected components. And for these two cases, the maximal case, the maximal value that can occur is, well, the length of these passes here, pass or cycle is simply the number of states, so this is this first factor, times the maximal utility value that you have in your Markov chain. And now, well, I mentioned before that we can approximate this supremum here using a binary search. So what we do is we pick as epsilon this value here and compute an approximation of the quantile, which simply means that this wanted value C over D minus P, well, the absolute value is bounded by epsilon. And now we rely on known results from mathematics. The quantile, the value we seek for, this C over D, is the so-called best rational approximation of this P, where the denominator is bounded by capital D. This means the following: whenever you pick a rational number that is in epsilon neighborhood of this approximation P, and where this rational number, A over B, the denominator B is bounded by D, then this AB equals CD. So this is a result of mathematics. Now what we do now is we apply the continued fraction method of P to compute the C over D, and this works as follows. This is just to remind, this is the continued expansion of, you can do this with any rational number. The P can be written in such a form, and the continued fractions, or this generates a sequence, or P1, and the next value P1 plus 1 divided by P2, and so on. And what is known is that these continued fractions, they jump around the P. Convergence is fast, which means eventually we reach this epsilon environment. And all these are rational numbers, these Q's. And also their denominators grow fast, grow exponentially. So eventually we will reach some value, let's say Q5, where the denominator is larger than D. So we know from then on the denominator will always be larger than D. And then what is known is either the previous value is exactly the C over D, or there is some closed formula how to derive this C over D from the previous and the element before. That there is some simple formula. There are two cases and you can check them. Well, and altogether this gives you a polynomial time algorithm to compute this value here. Well, this was the case where the probability for such a ratio invariance is positive, and you can also deal here with some conjunction with the phi being, for instance, a reachability or some Büchi condition, some repeated reachability condition, or some Rabin-Street condition. This street condition can be seen as a strong fairness constraint. Well, the point is you just need to check, let's say you need to reason about BSCCs. Again, there are good ones and bad ones. And for the bad ones, for this probability being positive, you can just ignore them. They cannot contribute to this probability.
Can phi just be a general LTL formula?
Yeah, but then in case you go via automaton, we do not get polynomial time anymore. But from the algorithm, yes. The algorithm still works.
So you just need the deterministic automaton?
Yeah. But this here, as stated, polynomial, then the polynomial would not be true.
If you have the deterministic automaton.
I mean, so if I attach here an automaton, you're right, yeah. So I mentioned before that we can also treat the case equals 1. Well, and this is even simpler. We do not need the continued fraction method. Probability of a conjunction of events is 1 if and only if the probabilities for both events is 1. So we can split it. The probability for this ratio invariance should be 1, and the probability for phi should be 1. For this one here, we can rely on standard techniques if the phi is a standard formula, be it an automaton, be it LTL, or as stated here. And the probability for such a ratio invariance without the phi is 1, if and only if there is no path from S where the ratio exceeds this value R. Now, if the R here, if you consider this to be a fixed value, then this is the case if and only if S does not have a path where the weight gets less or equal 0. And here this weight R, I mean this this weight function you have seen before, though the cost minus R times utility. And this was, let's say, these cases are, well, somehow I found it surprisingly, but yeah, well, whether it's a surprise or not. These invariances are harder than the cases when reasoning about some kind of long-run ratios. So, for instance, in this combination, always eventually, which means infinitely often, the ratio should be larger than R and some side constraint, or infinitely off. Here, would be the qualitative case, or this would be the case where we compare with some rational value Q. Here we have, even for this quantitative case, we have algorithms, and the point is, with this long-run constraint, we can again just look for the bottom strongly connected components. We know they have some well-defined long-run ratio, and we know almost all paths have this, that their long-run ratio is this expected long-run ratio. That's easy to compute. This was this LR RUT B, this B being a BSCC. Well, here by saying a good BSCC, I mean one that fits with this phi. And then what we seek for this supremum, it is simply the minimal value R, where the probability to reach one of these good BSCCs exceeds this value Q. And this one can be done in polynomial time. So in this context, reasoning about long-run things is simpler than reasoning about the invariances. Well, simpler, at least conceptually. And for if you say here, these are only the qualitative cases, I have no answer. If you ask a thing like this, whether this value exceeds 1/2, I don't know. Maybe it's decidable, maybe not. I simply don't know. Yeah, so this was the end for the lecture today. So tomorrow I will start, so I will skip this section on conditional probabilities. Tomorrow I will start with this combination of probabilism plus non-determinism, and then talk about the model of Markov decision processes. Thank you.
Very much.